All right, so this week we're talking about the greenhouse effect, the basic process that drives anthropogenic or human-caused climate change. So what we're going to be learning about in this lecture is first that you'll be able to explain the factors that make up the Earth's energy balance, because that's fundamentally what the greenhouse effect is about, is altering the energy balance of the Earth. Then you're going to understand how greenhouse gases are responsible for warming the Earth, and then identify some of the human and natural causes of climate change. So I mentioned energy balance, and so that's our starting point, that there's energy coming into the Earth and there's energy going out from the Earth. And our energy balance is the ratio between this energy in and out. The energy that's emitted by an object depends primarily on its temperature. So the hotter an object is, number one, the more energy that it emits. So hotter objects are giving out much more energy than colder objects. And the energy that comes off of a warmer object is also going to be at a shorter wavelength. So when we're looking at the electromagnetic spectrum, right, we've got different wavelengths of energy at different points on that spectrum, different kinds of energy that have different wavelengths. The warmer an object is, the shorter the wavelength of the energy that it's giving off. And you can see that illustrated there in the diagram. These are the emission curves for the sun and the Earth. So this is what kind of energy and how much of it would the sun and the Earth give off. And so the first thing you can see is that the sun is giving off way more energy than the Earth. And in fact, on this diagram, it says it's scaled down, right? So this diagram should actually be so tall you could, go right off the screen here, or you squish it down and you could hardly see the Earth thing there, right? So the sun is just emitting massively more energy than the Earth. And the sun's energy is also coming out at shorter wavelengths. Because the sun has a much higher temperature. Specifically, the sun is about 5,772 degrees Celsius. Right, so that's really hot. And so the sun's energy is mostly landing in the visible spectrum. So that little slice of the electromagnetic spectrum where our eyes can detect that radiation, and then we use it to see, that's the wavelength the sun is primarily emitting energy at, and that's why we can see that. And that's why that portion of the electromagnetic spectrum is visible, is because that's the main one that the sun is shining on us here on Earth. So our eyes have evolved to detect that kind of radiation, right? The eyes wouldn't be as useful if they were detecting some other kind of radiation that we don't have very much of that around. Right? So the sun is giving us a whole lot of this shorter wavelength, visible light spectrum energy. Then the Earth, being a much cooler body, is not only emitting less radiation overall, but is mostly emitting it at a longer wavelength. And specifically, the Earth is mostly radiating energy out in the infrared part of the electromagnetic spectrum. And our eyes can't see infrared. We can't detect that with our eyes, but we can feel it in the form of heat. So we can feel that energy as heat, but we don't see it. But it's just different wavelengths of energy on that same electromagnetic spectrum. And this energy that's coming in from the sun, we refer to as insolation. So that is smushing together of the words incoming solar radiation. So incoming solar radiation, energy coming to the Earth from the sun, we call that insolation. And insolation helps us understand the different climates and seasons that we have on the Earth. So as that energy is coming from the sun to the Earth, for all practical purposes, we can imagine the rays of energy coming in essentially parallel to each other, because the sun is about 109 times wider than the Earth, right? The sun is just massive. And so, those rays diverge a little bit as they radiate out from the sun, but by such a little amount over the tiny little space that the Earth takes up, that for practical purposes, we can think of them as coming in parallel to each other, striking all the parts of the side of the Earth facing the sun in parallel. So when the surface of the Earth is roughly perpendicular to those rays, they're coming down straight from overhead, you're going to get very concentrated energy from the sun. So that ray of sunlight is hitting a fairly small area when it hits a perpendicular piece of the Earth's surface, which is going to tend to be around the equator, right around the middle part of the Earth. But as the surface of the Earth curves away from the sun, and as we're looking at it on the side here, the surface of the Earth being a round object, it curves away from where the sun is. So that means the rays coming in there, they're coming in at a shallow angle, right? The sun is going to be low in the sky from the perspective of someone standing near one of the poles of the Earth. That same sort of ray of light is going to get spread out over a much bigger area of the Earth's surface. And if you look at the size of the area illuminated by one of those rays near the poles versus one near the equator, spread out over a much bigger area of the Earth's surface. So that means you have less solar energy per unit of area. Right? The energy is less dense. There's less of it in any one spot when you're closer to the poles. Thus, one of our very basic elements of climate, that it's warm near the equator and it's colder near the poles, and in between when you are in between. That's primarily due to the angle at which the sun's rays are hitting the Earth. They're hitting at a low angle and getting very spread out over a large area. When you are on the part of the Earth that curves away from the sun, they are very concentrated over a small area when they're coming down and hitting a surface that's fairly perpendicular. This also plays into why we have seasons. So the axis of the Earth is tilted about 23.5 degrees. So we are not spinning straight up and down relative to our orbit around the sun. We are sort of tilted to the side, like a spinning top that's starting to lean over. And that tilt is not tilted relative to the sun, like that we're pointed towards or away from the sun. We're tilted so that we point towards a particular point in the larger universe. And at the current time, this changes over the course of millions and millions of years as things in the universe move around. But at the current point in time, the north end of our axis points roughly toward the star Polaris, the so-called North Star. Very convenient for navigating in the northern hemisphere, where you can just look up, see where that star is, and that's north. In the southern hemisphere, you have to kind of triangulate that point from the other constellations that are around it, because there's no no visible star at least, directly in the direction that the south end of the axis points. And since we're pointing at the same spot in the universe all the time, that means as the Earth rotates around the sun, sometimes the northern hemisphere will be tilted toward the sun, right? If we're on the opposite side of the sun from where Polaris is, the northern hemisphere is going to be tilted a little more towards the sun, which means that the northern hemisphere is getting those more direct up and down rays from the sun. The southern hemisphere is getting the shallower angle spread out rays from the sun. Then as we orbit around the sun, we get to the other side of the sun. And so now the sun is behind us as our axis points towards Polaris in the north. And so now we get the opposite. So now the southern hemisphere is tilted towards the sun. They're getting rays that are coming down more overhead, more concentrated, more energy per unit of area. And the northern hemisphere is tilted away. We're getting shallower angle rays. They're more spread out, so less energy per unit area. So whenever your hemisphere is tilted towards the sun, you're going to have summer. It's going to be warmer overall. You're getting more energy, more insolation. When your hemisphere is tilted away from the sun, you're going to get winter. You're going to get less energy, more spread out, and it's going to be colder. And so this tilt is why our seasons are opposite in the northern hemisphere and southern hemisphere. So I'm recording this at the beginning of November. It's getting colder. Well, not today, but in general, it's getting colder. We're moving into winter here in the northern hemisphere, and so the opposite's happening in, say, Australia, where it's getting warmer. They're moving into their spring, into summer at this moment in time that I'm recording this video. So the tilt of the Earth and how that changes the angle of that insolation is one of the major reasons for the change in temperature as we go through the seasons. The other big reason is change in the length of the day, because the sun is going to illuminate half of the Earth, right? The half of the Earth that faces towards the sun is getting insolation. The other half is having night, no sun in the sky, no new energy coming in. And if you look at the diagram here, you can see that the line of illumination, the line that separates the day half and the night half of the Earth, does not line up with the axis. So that means that as we rotate around our axis, if you're in the hemisphere that's tilted towards the sun, you're going to spend more than half of that rotation within the illuminated half of the Earth. You're going to spend more than half of your 24 hours in the lighted portion. So you're going to be receiving insolation for the majority of your day. Now you're going to have a long daylight period where you're getting energy from the sun. When you're in a hemisphere that's tilted away from the sun, you're going to spend more than half of your rotation time in the dark half. And so you're only going to be getting solar energy for a small portion of your day. So you're getting not only weaker energy when you're tilted away from the sun because of the low angle that it's coming in at, but you're also getting it for a smaller portion of your day. So it's much less energy that you're receiving when you're tilted away from the sun, creates colder winter conditions, and then vice versa when you're tilted towards the sun, getting both more direct concentrated rays and getting them for a longer portion of your 24-hour day. One thing that's not playing a significant role here is our distance from the sun. The Earth's orbit is elliptical, with the sun at one of the foci of the ellipse, so sometimes we're farther from the sun, sometimes we're closer, but that doesn't make a big difference to our seasons. And in fact, the Earth is actually farthest from the sun during our northern hemisphere summer, and then we're closer to the sun during our northern hemisphere winter. So the seasons, it's a common misconception the seasons have something to do with our distance from the sun, but that's absolutely not true. It's about the tilt of the Earth and how that affects the angle of the sunlight coming in and the length of the days. So let's look at this energy coming in from the sun, right? We've got our insolation coming in from the sun. It's primarily visible light, so in that shorter wavelength portion of the electromagnetic spectrum. And as that insolation hits the Earth, there's two things that can happen to it. Some of it can simply be reflected off the surface of the Earth and go back out into space. So in this case, the form of the energy hasn't changed. It is still that short wavelength visible spectrum light. It just bounces off the Earth back out into space. So that's where you see the outgoing arrow. It's the same yellow color on the diagram there. Any of that energy that's not reflected is going to get absorbed by the Earth. And it gets absorbed by the Earth, it warms up the Earth, and then the Earth, as a body that has a temperature above absolute zero, is going to radiate energy back out. And as we said before, because the Earth is cooler than the sun, the insolation has not warmed the Earth to the sun's temperature. So as a cooler body, the Earth is going to radiate that energy back out as thermal radiation or infrared radiation, so at that longer wavelength. Okay, so we've got visible light coming in, some visible light reflected, other light gets absorbed by the Earth, re-radiated back out as infrared or heat radiation. And in the long run, the energy coming in will balance energy coming out. If they're not in balance, then the temperature of the Earth will change until they come back into balance. So if we start getting more insolation coming in and the excess isn't being reflected off, so it's all getting absorbed, the temperature of the Earth will increase until we're radiating that extra energy off equally as thermal radiation. If the amount of insolation were to decrease, then the Earth's temperature would drop until the thermal radiation came down to balance that out. So in the long run, the shifting the temperature of the Earth will balance out the energy coming in with the energy coming out. So as I mentioned, some of that insolation is getting just reflected back into space. It's not getting absorbed by the Earth. It's not getting re-radiated by the Earth. It's just bouncing off. And to describe the amount of that reflecting of energy that's going on, we use something called albedo. So albedo it's a pretty simple concept. It's simply the percentage of insolation that's reflected by the surface of the Earth. Right? So it's a number between 0 and 100. What percentage of the insolation that hits the Earth gets reflected back out into space, still in the form of shortwave visible light radiation. Another way to think of this is it's the shininess of the Earth, right? The Earth is shiny, it's reflecting a lot of that energy away and absorbing very little. If the Earth is not so shiny, it's absorbing more radiation and reflecting less of it. And the albedo of the Earth depends on whatever is covering the surface of the Earth wherever this insolation is striking it. So we have sometimes very different albedos between different parts of the Earth's surface, and that's what you can see on the chart there. So some of the highest albedos are things like fresh snow or various types of clouds. So cumulus, stratus, altostratus, cirrus, those are all names of types of clouds. And so if you're thinking about, well, what does freshly fallen snow and clouds have in common? It's that they're very light colored, right? Those are white things. And so that's what the color white is. It's when most of the light is getting reflected off of an object, we see that as the color white. So light colored things tend to have very high albedos. And then as you go down the chart, you'll see darker and darker land surfaces having lower and lower albedos, right? So you have fresh snow and then old snow, right? Because old snow starts to get a little dirty, starts to get a little off-colored. It's not as white and shiny. It doesn't hurt your eyes to look at because it's not reflecting so much energy off of it. And sand and ice are a little lower albedo than that. So wet sand, right? Wet sand is darker than dry sand. Dark wet soil, a forest, right? Those are even darker. Water is very dark colored. So those are absorbing most of the insolation that hits them rather than reflecting it away. So that means that if we change our land surface, we can alter the albedo, and that alters our energy balance, and that can alter our climate at both the localized scale and the broader scale. And so one way that we see that is with what's called the urban heat island effect, because a lot of the surfaces that we have in urban areas tend to have very low albedos, especially as compared to whatever might have been there before. So, asphalt, for example, if you've got big paved areas like parking lots and roads and stuff, right? Those are very dark colored. That's going to have very low albedo. It's going to absorb lots of the insolation. Dark roofs, right? Shingles on roofs are usually dark colored. It's going to absorb a lot of that radiation. It's not going to reflect very much away. And so that's going to raise the temperature locally where all those dark surfaces are located. So that tends to make temperatures in urban areas several degrees warmer, sort of consistently through the year, than in surrounding rural areas that tend to have higher albedos. On the flip side, if you notice on the chart where crops is located, it's 20-ish percent albedo, and you compare that to, say, forest, which has maybe that 10% albedo. If we were to cut down a forest and replace that with crops, right? Make a farm in that location, or you can see savanna and meadows there also having higher albedos than a forest. So if we turned our forest into like grazing land for cattle, for example, right? These are very common large-scale land surface changes that people carry out, right? We cut down a lot of forests and replace them with these other kinds of uses of the land. When we're doing that, we are raising the albedo. So we're causing that land to reflect more of that insolation back out into space, and so that's going to have a cooling effect, right? Not as much of the energy is going to get absorbed by the Earth and then increase our temperature and get re-radiated as longer wave infrared or thermal radiation. So we can change the albedo in either direction. Right? We can make our land surfaces darker, lower albedo. With a warming effect, we can make them lighter colored, higher albedo, cooling effect. So we can use what we've learned here to calculate what the temperature of an object should be. And I've put up on the screen there a equation that we can use for that. And so in this equation, we've got T means the temperature of the Earth, and in this equation we measure that in degrees Kelvin. So Kelvin is the scale where 0 is absolute 0. It means something has no temperature. The molecules and atoms in that thing are completely frozen in place. They're not moving at all. So there's 0 temperature. It's the coldest something can possibly be. That's 0 Kelvin, and then it goes up from there. Degrees Kelvin are the same size as degrees Celsius. It just has a different 0 point here. So the temperature of the Earth in Kelvin is going to be a function of, first, S, which represents insolation. So that's more solar energy, I think is why they call it S, right? So it's a function of that, the energy you're getting, and your albedo, which reduces that energy by a percent based on how much is just getting reflected off. Right? It's not going to get absorbed by the object that you are heating. So you've got S times 1 minus A, so S times the percentage of it that's actually getting absorbed. Then you take the fourth root of that, which is just a function. That's the relationship between energy and temperature, times 45.8, which is called the Stefan-Boltzmann constant. That's just like a physics fact. That's just one of these constants, one of these numbers that describes how our world works. But if you multiply that out, that would tell you what the temperature of the Earth would be once this system gets all into balance, right? You give it a little time for the temperature to change based on the amount of energy you're getting, and this equation would allow you to figure that out. I am not going to ask you to solve this equation. I am not going to give you numbers and ask you to plug them into the Stefan-Boltzmann law and calculate things out. I'm putting the equation up here because I think talking through what goes into this equation helps us understand what's going on, right? Helps us understand the physics at play, helps us understand the relationship between these different factors. But you're not going to have to do the math on this one. Don't worry about that. So this is a pretty basic physics law. This is well-established fundamental piece of physics, is this relationship between the energy that an object is receiving and the temperature that it will end up at in equilibrium. And so if we plug into this equation the amount of insolation that the Earth receives and the average albedo of the Earth, what it tells us is that the Earth's average temperature should be negative 18 degrees Celsius. So obviously that's going to be different in different parts of the Earth, right? The areas that are getting that direct overhead sunlight and that are having longer days are going to be warmer. The areas that are getting the lower angle sunlight and having longer nights are going to be colder. But if you average it all together, according to the Stefan-Boltzmann law, our average surface temperature of the Earth should be negative 18 degrees Celsius. But of course, we can measure the surface temperature of the Earth. And if we measure the surface temperature of the Earth, it is actually an average of 15 degrees Celsius. Positive 15 degrees Celsius, right? So 33 degrees warmer than the Stefan-Boltzmann equation tells us that we are supposed to be. So clearly there's something that we're forgetting. There's something that's not being taken into account here when our calculation using this basic physics law is telling us that we ought to be 33 degrees colder than we are in reality. And so here's what we're forgetting. We're forgetting when we do that equation that the Earth has an atmosphere. The Earth has this additional layer of gases around it. On the diagram here, of course, the size of that atmosphere is wildly exaggerated just to sort of show you conceptually what's going on. So we've got our insolation comes in. Some of it gets reflected off the Earth, goes back out as shortwave visible radiation. The Earth absorbs the remainder, radiates that back out. But as that thermal radiation, that infrared long wave radiation is being radiated out from the Earth, some of it is going to get absorbed by the atmosphere. So it's not just going to fly back out into space. It's going to get absorbed by the atmosphere. And then the atmosphere, just like the Earth, absorbs that energy and then re-radiates it back out, still as thermal infrared long wave radiation, still in the same vicinity in the electromagnetic spectrum. But when the atmosphere radiates that energy back out, it's going to radiate some of it out into space and some of it back down to the surface of the Earth. So some of this energy that came in from the sun is now going to bounce back and forth between the atmosphere and the surface of the Earth. It's not going to escape the system. And so that's going to keep the temperature on the surface of the Earth much warmer than it otherwise would have been. So the temperature at the outside of the atmosphere, at the outside of this whole system, is in fact negative 18 degrees Celsius. But the temperature at the surface of the Earth, right, where we're standing on the surface of the Earth, below the atmosphere, is significantly warmer because that atmosphere is trapping some of that energy. And so the process by which that atmosphere traps some of that energy is known as the greenhouse effect, because it's more or less the same principle by which a greenhouse remains warm during the winter. The glass in the windows of a greenhouse functions the same way as greenhouse gases in the Earth's atmosphere. So most of the atmosphere, if you remember back to the last lesson, right, most of the atmosphere is made out of nitrogen and oxygen. And nitrogen and oxygen generally let energy of any wavelength just pass through them. So you get that shortwave radiation coming in from the sun. It goes right through our oxygen and nitrogen. And then you get your infrared thermal radiation, longer wave radiated back out from the Earth. It goes right through your oxygen and nitrogen as well. Okay, so that energy just passes right through there, same form with those gases. But some other gases that are in our atmosphere are transparent to that shortwave visible light radiation coming in. So they'll let all the insolation come right in to the surface of the Earth, but they are not fully transparent to that longer wave radiation. So as the radiation is coming back out from the Earth, it will get absorbed by these gases and re-radiated, some back down to the Earth, some out into space. So these greenhouse gases that have this property that they allow shortwave radiation to pass right through them, but don't allow thermal radiation, infrared radiation to go through them, include carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, and water vapor, H2O, plus a whole bunch of other ones that are not as common. There's not as much of them in the atmosphere. So those four are sort of the big ones, the ones that have the most impact on the Earth's climate. Carbon dioxide, methane, nitrous oxide, water vapor. And one thing you may notice is that those are a little bit more complicated molecules than oxygen and nitrogen. So oxygen in our atmosphere is usually found in the form of O2. So it's just two oxygen atoms stuck together to make a molecule. Nitrogen, likewise, is mostly N2, so it's two nitrogens stuck together to make a molecule. Third most common gas that I didn't put on the slide there, but argon, that's makes up most of what's not oxygen and nitrogen, is also not a greenhouse gas. That's usually present in the form of just a single atom of argon all on its own. So these are very simple molecules. But our greenhouse gases are more complicated molecules, right? You've got multiple different elements making them up. They have a more complex chemical structure. Their molecules are asymmetrical. And so because they're more complicated molecules, they're more reactive to this longer wave energy that's going through. It allows them to absorb that energy more than those very simple molecules like oxygen, nitrogen, argon would do. And some of these other greenhouse gases that aren't listed on that slide are even more complicated molecules and are even more powerful greenhouse gases because they're such complex molecules. So that's what's happening here with the greenhouse effect, that we've got these gases that, even though they only make up a tiny fraction of our Earth's atmosphere, are absorbing this outgoing radiation, radiating it back down to the Earth, keeping the Earth warmer than it otherwise would have been. And this is a natural process. This is something that has existed on the Earth for billions of years. It's made it possible for life to exist on Earth. If the surface of the Earth was that negative 18 degrees Celsius, we probably wouldn't be here. There wouldn't be living things because the water would stay frozen everywhere. Wouldn't be able to support life. So the greenhouse effect is an essential natural process for our Earth. However, it's a process that has been amplified by human activity. So people have taken this greenhouse effect and put it into overdrive by adding excessive amounts of these greenhouse gases into the atmosphere. So we've ramped up the greenhouse effect, and that is what's producing our climate change. So here's a little more in-depth diagram of this process of energy coming in, energy going out. So on this diagram, if we look at that first row, that is showing the radiation coming in from the sun in red, going out from the Earth in blue. And you can see where it lies along that the electromagnetic spectrum there, right? You can see that the solar radiation is mostly in the visible part of the spectrum. The radiation coming out from the Earth is mostly in the infrared, longer wave part of that spectrum. The nice smooth curves that are drawn there are the theoretical predictions based on things like the Stefan-Boltzmann law. So that shows the energy that ought to be coming out of the sun or coming out of the Earth. Then the more jaggedy thing underneath it that's colored in solid is the actual amount of radiation that's getting through the atmosphere. So what you can see is when you look at the sun, it looks like most of the sun's energy is coming into the Earth's surface, right? There are a few little wavelengths where it drops down a little bit. It doesn't completely fill the area underneath that nice, smooth theoretical curve. The biggest one where you see some white space there, energy not making it to the Earth, is in the ultraviolet part of the spectrum. So even shorter wavelength than visible light. The sun emits some of that UV radiation. That's the main one that's missing as it comes down to the surface of the Earth there. But for the most part, most of that solar radiation is getting through. Right? There's nothing blocking most of the insolation energy from reaching the Earth's surface. However, when we look at the curve for the Earth, we've got that nice bell curve in blue there. That's what the Earth ought to be radiating out. But we see what actually gets through the atmosphere is much, much less than that. Right? We've got that jaggedy blue thing. So, in some wavelengths, we're emitting quite a lot of radiation, but in other wavelengths, almost nothing is actually getting through the atmosphere back out into space. So those greenhouse gases are taking big bites out of that outgoing radiation from the Earth. They're preventing a whole lot of it in a lot of those wavelengths from escaping through the atmosphere. And so below that, the next row shows the total absorption by all the different components of our atmosphere. And then below that, those smaller rows break it down by the specific gases. So you can see which wavelengths water vapor is absorbing. Okay, so you see water vapor is responsible for most of those little divots in the incoming solar radiation, the insolation. Some of that is blocked by the water vapor, and water vapor also takes some big bites out of the outgoing radiation from the Earth in blue. Carbon dioxide also taking some big chunks out of our outgoing radiation. You've got oxygen and ozone there, and you'll notice the main thing that's doing is that's what's blocking that UV radiation from the sun. Right? The sun is putting out radiation in the ultraviolet spectrum. A lot of it's not making it down to the surface of the Earth. That's because of that ozone layer. So in the stratosphere, we have that layer where we have ozone, which is a form of oxygen where the molecule is made up of 3 oxygen atoms. So normal oxygen, what we're breathing in right now, is O2, 2 oxygen atoms together in a molecule. Ozone is O3. It's got 3 atoms of oxygen to make up a molecule. We've got kind of a layer of that up in the stratosphere. And so that's protecting us from that UV radiation coming in. That's the main thing that ozone is doing, right? It's not absorbing very much of the outgoing radiation. It's just blocking some of that incoming radiation. Then you see methane, nitrous oxide in there as well, each taking a chunk out of the outgoing thermal radiation. So all of that stuff that's not making it out through the atmosphere, that's what's being absorbed by these greenhouse gases, radiated back down to the surface of the Earth, maintaining the Earth's higher temperature. And that's the basic process of the greenhouse effect. So we can now dig into these specific greenhouse gases and look at what each of them is doing and how they compare to each other. And one way that we can compare different greenhouse gases is with what's called their global warming potential. So the global warming potential is how much warming is caused by this gas as compared to the same mass of CO2. So CO2, carbon dioxide, is our standard of comparison. Right? CO2 we designate as having a global warming potential of 1. So the warming potential of a kilogram of CO2 is the same as the warming potential of a kilogram of CO2, right? That's self-evident, I think. And so then everything else is measured relative to CO2. So how does it compare to CO2? So you'll see on the chart there, methane has a global warming potential of 28. So that means a kilogram of methane is going to cause 20 to 8 times as much warming as a kilogram of carbon dioxide, right? Methane on a gram for gram basis is 28 times more powerful than carbon dioxide. And generally speaking, carbon dioxide is actually one of our weakest greenhouse gases in terms of global warming potential. That's why we're using it. One of the reasons we're using it as the standard is because it's a nice low number, and then everything else is several times more than carbon dioxide. You can see nitrous oxide there is 265 times higher global warming potential than CO2. SF6, which is a very much more rare chemical, but when we do get it, it has 23,000 times the global warming potential of CO2. So CO2 has a very low global warming potential. But on the flip side, the reason we talk about CO2 all the time is because it's by far the most common greenhouse gas. It's the one that we put the most volume of, or the most mass of, into our atmosphere, right? So the SF6 is super powerful, but there's only a tiny, tiny little bit of it in the atmosphere as compared to the amount of CO2 that we're putting into the atmosphere. Another thing to factor in is also how long these gases will stay in the atmosphere, causing this kind of warming, because methane also breaks down and cycles out of the atmosphere quicker than carbon dioxide does. So methane's not as long-lived as CO2. So then another way to talk about these factors that are changing the Earth's energy balance and enhancing or unenhancing the greenhouse effect is in terms of radiative forcing. So radiative forcing describes how much change in the Earth's energy balance is caused by a particular factor. So how much is this thing that's happening on our Earth going to alter the Earth's energy balance? That's our radiative forcing. Right? It's forcing a change in the balance of radiation coming in and out of our Earth. So we can add up the various features of these factors and calculate the radiative forcing, and then sum all those together to figure out what the total radiative forcing is, and therefore how much our climate is going to change. So for a greenhouse gas, the radiative forcing is a function of its global warming potential. How much radiation is it going to hold in per kilogram or per gram or whatever, and its mass, how much of it is there in the atmosphere. So you can see in the first few lines of that chart, carbon dioxide, CO2, has the biggest radiative forcing of any factor that we're looking at here, because even though it has a very low global warming potential relative to these other gases, there's just so much of it that we put into the atmosphere. So what we're seeing there is radiative forcing by anthropogenic, human-caused, human-created CO2 in the atmosphere. And so the bar on the chart shows you our best estimate of the size of that radiative forcing, and then the little black bracket around it is a uncertainty range. Right? So that's shows that we don't have the exact number pinned down exactly. There's some wiggle room in that, but the bar shows our best estimate of the radiative forcing. So CO2, pretty big radiative forcing, warming the Earth. CH4, which is methane, you can see has a decent sized one because methane is a more powerful greenhouse gas, even though we're putting out less of it. Then you see halocarbons, a class of chemicals that also has some functions as greenhouse gas, has some radiative forcing there. Nitrous oxides has a smaller contribution. Again, it's high global warming potential, but there's just a lot less of it that we put into the atmosphere, so that's why its overall radiative forcing is relatively low. And then we've got carbon monoxide, some other chemicals there. You'll notice that NOx there, so that's nitrogen oxide, actually has an estimated negative radiative forcing. So that actually has a cooling effect. And then in the next slot there, we've got aerosols. So these are things in the atmosphere that are altering our albedo. So they are things that can reflect away more of the sun's energy when they are in the atmosphere, or that can absorb solar energy in the atmosphere. And you can actually kind of see that if you look at the different colors of that first bar there. You'll see most of these aerosols, things like sulfate in yellow there, or mineral dust, those have a negative radiative forcing. They are cooling the Earth because they're light colored, they're reflecting solar energy away from the Earth, raising our albedo, cooling the Earth. But then the part that sticks out on the positive side, that's black carbon. So when we have like soot that gets into the atmosphere that's very dark colored, that's dark color means it's going to reduce our albedo. It's going to absorb more energy, so it's going to have a warming effect. So these aerosols, these things that are changing the albedo in our atmosphere, most of them have a cooling effect by raising the albedo, but black carbon goes the other way. And then you'll see albedo due to land use change. So that's things like cutting down a forest and replacing it with pasture land for cattle, or with, a field of corn or soybeans or something like that. And as we said a little while ago, that tends to raise the albedo. It tends to make the Earth's surface lighter colored, and so that's going to have a cooling effect. And you can see the negative radiative forcing on the chart there. And then the last little bar there is changes in solar irradiance. So this is the one natural process that makes a difference to our climate over the short time frame that we're looking at here, which is the changes in the amount of energy we're getting from the sun. And you can see that changes in solar irradiance are actually having a tiny little positive radiative forcing. The sun is giving us just a little bit more energy, though, as compared to the radiative forcing of all these other anthropogenic factors, right, of land use change, aerosols in the atmosphere, CO2, even nitrous oxide, all of these anthropogenic factors, all these human-created factors, are much bigger than any natural phenomena. And then the last part of the chart there just adds up all the anthropogenic factors and shows where they were at 3 different points in time. So 1950 versus 1980 versus 2011 when this chart was put together, or when the data for this chart was put together. And so you can see this increasing anthropogenic radiative forcing over time. So the sides of these bars are becoming farther out to the positive side as time goes on. And the more radiative forcing we have in the positive direction, the warmer the Earth is going to get. The more energy is going to be trapped in the atmosphere and increasing our surface temperature of the Earth. So with all that in mind, your lab assignment for this week, you're going to be looking at some simple models of the Earth's energy balance. So some computer models, they run in your web browser because they're fairly simple models. The equations behind them are not factoring in a huge amount of different feedbacks and little things that go into the most sophisticated climate models, but they made it so that you can run it in your browser just to get a basic idea of the relationship between these different factors and the Earth's energy balance and the Earth's temperature. So you're going to be looking at the effects of changing the amounts of greenhouse gases and changing the albedo of the Earth, and how that alters the Earth's energy budget, the energy balance, and the temperature of the Earth. So that's what you'll be doing for your lab exercise.